them try to poke holes in it. And when you're solid at that point, then do the C++. So to that end, right, I'm gonna draw what happens when you insert, and we're gonna talk about the whole process of propagating, splitting up a tree. But I'm not gonna write pseudocode because that really is an important part of the lab. It's important for you guys to do that. So I'm gonna draw part of a figure in the book that starts on page 674. It's figure 14.13. It's a huge B-tree, so I'm just gonna well, it's not huge, but it would take up like the whole board, so I don't wanna draw the whole thing because it would be a waste of everybody's time. But just to start out, so if you guys wanna follow along, figure 14.13.
Let me find some chalk.
No, this is fine. Let's do this over here. Can everybody see this well? Is that okay if I draw it like that size? Okay, cool.
Not saying you have to do this. Never mind.
Okay, so there's this is one slice of a B-tree. So this is an interior node, it's not a root, and these are two leaves. Okay, so hopefully you guys are all cool with what I've drawn here, but I'll just take a quick second to explain what's going on, right? So these are all keys that we have at the leaves, right? And the order of this B-tree is 3, so we've said that a leaf can store 3 keys, right? And that means that a node also has 4 pointers, 3 plus 1. The first 3 pointers point to, at the leaf, the value corresponding to this key. And then the last one points to potentially the next node if there is one at that level. So here, right, this points over here. Here, this is like a null pointer, so it's a little bit misleading. Okay? So our task here is to insert 40. Okay? So my goal here is to show you that if you can reason about what you need to do at the leaf, and if you can reason about what you need to do at the next higher level, you actually understand everything that you need to do all the way up the tree. Okay? So, can anybody explain what they think the first step would be to insert 40 into this?
Can you try and push up the chalkboard? The top one? Yeah, okay. Alright.
Okay, you guys know this. What's the first thing that it's going to do if I say insert 40? Yeah.
We try to insert it into the leaf
Good, okay, so let's start with that. So that was all correct. So it traverses potentially from the root, comes from all the way over here, and it says, okay, we get to this node, right? It's going to traverse over this thing. See, 23, is that greater than 40? No. 31, is that greater than 40? No. 43 is greater than 40. So go back to the previous one and follow its pointer, okay? And then it's going to traverse this thing. Is 31 greater than 40? No. 37? No. 41? Yes. Okay? So that's the process of how it figures out that it needs to insert here. So is everybody cool with that? Okay. So the first thing basically that it's going to do is just split the leaf. Okay? So so we'll keep this the same. Right. Okay, so what do the new leaves look like? It's a really easy question. Someone answer. It splits this node into two nodes. What do those two nodes look like? Someone else. Yeah.
31, 37, and then it's 44.
Good. Yeah. So it's not that hard. Okay. So draw those. Okay. Now what? Okay, so I'll walk through a little bit of it. Okay. So now you need to make sure that if you go up the tree, everything points to things, right? So like the overall abstract notion of the rest of this is if there is a node, something at the level above it has to point to it. Okay? So that's really the notion that guides this whole algorithm. Okay? So is every leaf here pointed to if we don't change anything at the higher level? Yeah, I see no. Okay. Which one do we have to figure out? Like which one wasn't accounted for? Yeah. Yeah, exactly. So if we look at this, right, we have the 43 pointing over here, and we have the 31 pointing over here, and nothing points to 40. Okay? So what you need to realize at this point is that the rest of the algorithm is pretty much exactly the same as previous parts of the algorithm. So previously we said, okay, we know we need to insert at like this general location. Like if we can find, like we know we need to insert 40, if we can find the two nodes where 40 is right in between the two, or the two elements where 40 is right in between the two, we know where to split. In this case, it's really exactly the same thing, right? So you go back up the tree, and you see, okay, something needs to point to 40, right? And if we're at this node, so there are many different ways that we could get to this node, but like in the most naive implementation, we'll go all the way back up to the root and search until we find a 40 at the level above the leaf level, right? and we'll go through and we'll see 23, is that greater? No. 31, is that greater? No. 43, yes. Okay. And then what? So I'll give you a hint. It's exactly the same as what before. What do we do with this node? Yeah.
You're gonna split it on 23, 31, 40, 42.
Exactly, yeah. So then we go into this and we say, okay. We look at it and we say there isn't enough room to insert a new element into this node. And we say 23, 31, an empty thing. And 23 points somewhere over here. 31 points to this. And that's free for now. This points over here. 40, 41. Sorry.
40.
And now everything's pointed to. So if you needed to, like, so the same thing then happens if this tree were bigger and we needed to go further up the tree. I think in the case of the books example, yeah, with the figure that they provide, you can just, I think they provide a node with enough space to just be able to, like, write a 40, like it looks something like this. But it's the same thing at every level, right? What we're gonna say here is, okay, this starts with 23. Is there something that points to this? Yes, because this already existed, right? Is there something that points to this? No. We're going to go one higher level in the tree, find the node that needs to point to it, see if we can insert. If we can, great. If not, split. So there are different ways to write this algorithm, but the idea is that, the general idea is that you split at the leaf, and then you propagate that split upward, just checking to make sure that everything is pointed to. And since you're basically doing the same type of computation, you're just changing it at what level of the tree it happens, it's natural to write this thing recursively. Yeah?
Did you add that 400 thing that in the end, or?
Yeah. I think. Actually, maybe not.
Happens on a split.
Yeah, no, actually that was wrong. Intermediate nodes don't have this. Okay, so if you want a walkthrough of this in the book, the initial tree that they use is figure 14.13 on page 674. Okay, and then they walk through this graphically. Well, so they explain it as it's section 14.2.5, starts on page 678. Then this second figure, when they're actually doing the insertion page, shoot, I'm giving you guys the wrong page numbers. Sorry, my PDF is all screwed up. It's so it starts at figure 14.13, then look at figure 14.15, that explains how you split the leaf. And then you go to figure 14.16 and it shows how you propagate this back upward. So I think this is a really good example. Yeah, I'd refer to it when you're confused about how to split. Yeah?
I think like in some places, like in the book among PDFs, it talks about how like the leaves should be like between half full and like totally full.
Right.
Does that like matter? Like if we wanted to insert like 36 into the one on the right, would we have to split once it gets full, or can we just like shift to 37 and stick 36?
You could. Is there anything wrong?
So think you could, so first of all, keep in mind that I think in the lab, the requirement is that they should just never be more than 2/3 full. Is that correct? Yeah. So in general, like a B-tree is kind of like this abstract data structure where you can impose different constraints on it. If you're going to impose that constraint, then you could, I think, just move this 37 over. In the lab, you never have to worry about that because the rule is just it should never be more than 2/3 full, so you can always split, I think. But I'll check on that to be certain. Yeah?
How do you know if you're at a leaf or an intermediate node?
Oh yeah, so that one in the lab is simple. The nodes are tagged, like they have this little, I think it's an enum, just saying whether it's a leaf or an interior node. More generally, like if you're looking at this data structure, interior nodes always, these pointers always point to, well, nodes at the lower level. They could be interior or leaf nodes, but these pointers point to disk. So, yeah. Okay, any other questions? Any questions about the lab or about lecture? In lecture, you know, we can do our best to answer, but. Yeah.
I don't know if this is looking too far forward, but let's say we have code for an update answer and we want to test that. If there's enough time, could I go over how you would do that? I know there's a test harness and like
Yeah.
ways testing, but it'd be helpful, you know, so I know you have like initialize like this, I think, and to run through.
Yeah. So I haven't run through how to manually write test cases, and also when I did this lab, I didn't write any manual test cases because basically the way the test harness works is that you can generate as many random test cases as you want. And so if you generate like several thousand random test cases, it's pretty likely that you're going to hit a lot of edge cases. As to how to specifically write your own test cases, I don't know yet because I haven't looked into that test harness yet, because as you noticed, there was a bug that needed to get fixed today. So, you know, been waiting for the final version of that. Yeah, so I guess for manually writing test cases, like I agree, it's good to write your own test cases. I'm gonna have to get back to you on that one though. Yeah, actually reminds me, one small point. I think, so this is something that Professor Dindo wanted me to mention. I think if you want to use the visualization tool provided by the B+Tree lab, which I truly don't, I have not tried to use, by default, I think your disk size is set to 4 megs. That's going to be so big that you're not going to be able to use the visualization tool very well. Just if you want to use that, restrict your disk size to be quite a bit smaller so that you can make a small enough tree to reason about it. Yeah, and then another piece of advice, so look at the output when you run the test harness, the testme.pl code. So in the past, there was a known bug where basically if you segfaulted on certain operations, it would still say that the test passed because it's just comparing output from standard out. I think that's been fixed, but it's always possible that there are bugs, right? It's software, there are gonna be bugs. So make sure to look at the output of that thing to verify that your tests actually passed. Yeah. So any other questions about anything? Like anything at all? Yeah.
Just a quick one. For B+Tree, that CC at the bottom, there's a function called print. It says correct me, but in the actual document for B+Tree, it doesn't say anything about print. So I'm not sure if that's something you have to do or not.
What do you mean have to do?
Because in the print, if there's function print in it, there's a comment that says correct me.
Okay.
In the actual lab assignment.
Right. Yeah, I don't think that you, so I don't for sure know the answer, but I think that that's just there for debugging. Like if you want a way of like pretty printing your B-tree, it can help you debug, but I don't think it's a requirement. But yeah. Cool. Anything else? All right. So yeah, I guess like echo like general piece of advice. Like C++ is very low level code. It's not good for thinking, right? So like sometimes if you write like Racket or Python or Perl or something that's more high level, you can kind of think as you code. But C++ like pretty bad for that. So I really, really, really want to emphasize that you should write pseudocode and debug that before you write your C++ code. And when you're writing your pseudocode, just don't worry about like the serialization and the unserialization. That's the point of writing it. It's just like, think about abstract data structures, and also like this type of problem is kind of like an interview problem, right? So this is good practice if you want to do technical interviews, like how do you traverse a tree when you need to do certain things. So it's good to whiteboard it with your partner. Yeah, think before you code. Great piece of advice that was given to me by one of the professors here. Yeah, cool. That's all I got. Post on Piazza if you have any other questions.